Which of these species is the largest and which is the smallest? Could you rank them all in order? Let's talk about ionic radius. So I had just recently posted a video about atomic radius, and now it's the same idea, but ionic radius. So if we understand atomic radius, we know that looking at the periodic table, the elements get larger as we go down a group, and they actually get smaller as we go to the right across a period due to the increased nuclear charge, okay? Now, when we're looking at ions, though, things are going to change a little bit, and we should understand how atomic orbitals work and the principal energy levels, right? I also have a video on that, so check that out as well. So now let's jump in. And what we want to look at is thinking about how the electron configurations work, or the atomic orbitals. If we look at any of these species that I put here in my quiz, we can see that they actually all have the same electron configuration. And that is that of the noble gas neon. So if we take fluorine, and we have 9 protons and 9 electrons in the neutral version of the atom, then we add an electron, now we have a negative charge, right? So remember, electrons are negative, so if we have a negative charge, we're just adding an electron. So now we have 10 electrons and only 9 protons, that's why we have a net negative charge, all right? Now, if we look at fluorine and we add an electron to it, we go to the right one spot. So the electron configuration of fluorine is, with a negative charge, is the same as that of neon. Neon just is neon, right? And then if we go over here, nitrogen with a -3 charge is over here. If we add 3 electrons to nitrogen, 1, 2, 3, we have exactly the same electron configuration again as neon. And then if we go to aluminum with a +3, aluminum's here. If we take away 3 electrons, we're going to the left 3 spots. So 1, 2, and then 3. So all of these have the exact same electron configuration, but different charges. Now let's think about what's happening when we change our electron configurations here. Aluminum is the only one that I gave a positive charge to. So aluminum is in period 3. So it means that it's 3 valence electrons because it has the 3s2 and the 3p1, right? So it's also in group 3a, which means there's 3 valence electrons. So this has 3 valence electrons, so 3 electrons in the principal energy level 3, or electron shell 3. So when we give it a +3 charge, we're just completely getting rid of shell 3. So if we think about what that atom would look like, we'd have our nucleus with a bunch of protons and neutrons in that nucleus. And then just to make things simple, we're going to draw it like this. Let's call that principal energy level 1. This is going to be 2. And this is going to be 3. So when we give it a +3 charge, when we make this into a cation, which is a positive ion, right? We're straight up getting rid of the valence shell. And so we're getting rid of that shell 3 there. And so we are getting dramatically smaller, right? So if we compare an aluminum with a +3 to a regular aluminum atom that is neutral, the cation, the +3 version, is dramatically smaller because we just got rid of an entire principal energy level, the shell 3. Now, we have the same electron configuration as neon, but the nucleus is more highly charged. We have a higher atomic charge, a nuclear charge, rather, than neon does, right? So neon has the 10 electrons and 10 protons. Now this aluminum with a +3 has the same electron configuration as neon, 10 electrons, but it has 13 protons, right? It's number 13. And so it's going to be pulling a lot more strongly on that outermost shell now, or just on the electrons in general. That +3 charge that the atom has, or it's now an ion, is going to attract those electrons more strongly. And so an aluminum 3+ is not only much smaller than the original neutral aluminum atom, but it's also smaller than the element whose electron configuration it has, which is neon, okay? So all these I can draw with the electron configuration of just writing neon in brackets, right? And if you saw my video on electron configurations, this should make sense. We could also say 1s2, 2s2, 2p6. That's all saying the same thing. This is looking a little ugly. Let me try and fix that a little bit. So now we can see that the aluminum 3 plus has the same electron configuration as neon, but an excess of protons in comparison, and so is going to be pulling those electrons in more tightly. Now let's look at the other ones. So neon's going to be kind of our reference point for all of these. Let's look at fluoride. So fluoride has, again, like I mentioned, the same electron configuration as neon, but only has 9 protons instead of the 10 that neon has. So it has excess electrons, right? That's why it's negative. And so the nucleus is not going to be able to pull those electrons in as strongly anymore, because now we have an extra electron and they're repelling each other further. So if we imagine whatever the size of neon is, its atomic radius, fluoride, which is F minus, is going to be a little larger now because that negative charge is causing the repulsion of those electrons and the nucleus can't hold them in as tightly. And then if we just exaggerate that, nitride, which is N with a -3 charge, is going to be even larger because now you have a -3 charge on it. So the electrons are really repelling each other. And you have, basically, we again have the same electron configuration as neon, but we're missing 3 of the protons that neon would have. So it's just not able to contain everything. And that's going to spread out even further and be larger. All right, guys? So if we take a look at this, they all have the electron configuration of neon. That's going to be our reference point. And we know that the aluminum ion is going to be smaller. And then neon is the neutral one. And then fluoride only has a single negative charge. And then the nitride has a -3. So going from smallest to largest, we have the aluminum, then the neon, then the fluoride, and then the nitride. Guys, if this lesson helps you, please give a like, follow, share this with others that could use the help, save it so you can review again later, and please consider patronizing me over here. That helps me to continue making these videos for free. So stay tuned for the next lesson, and I'll see you guys there.